Hello, everyone. I'm Ken Yeang, and I'm going to talk about the work I've been doing for the last few decades. It's essentially about designing for a resilient planet. Our work is essentially experimental, and I'm going to show the experiments we've done to advance the field of ecological design. A quick description of our methodology is very simple. Right? We do research. We are a research-based architect company, and from there we derive generic principles and concepts, interpret these by design, and we build the propositions as prototypes. Then you evaluate, discover, and advance the principles, and this gives feedback to the generic principles and concepts. And we publish it. We publish it. I've authored about 12 books, and this leads to improvements to what we are working on, and then to more research. So now we see ecological design as a set of infrastructures. There are 5 infrastructures: nature, people, the built environment, energy systems, hydrology. Built environment is a term we use to refer to everything that human beings make. It includes technology, artifacts, food, and anything that humans make. And so nature is ecosystems and the biogeochemical cycles in the biosphere. People is our social, economic, political, institutional systems. The built environment consists of the artifacts, structures, the infrastructures, technology, food products, energy systems, renewable. We try to achieve zero emissions and low embodied energy content, and hydrology, which is essentially water management and conservation. Now, represented graphically, these are the 5 key factors: nature, human beings, the built environment, energy, and hydrology. And these are the objectives of each one of these. In nature, we try and achieve net positive ecological impact. For human society, we try and enhance the net well-being and create a happy society if we can. For water, we try and have net zero water with conservation. And with structures and infrastructure, we try and have net zero waste and emissions. And for energy systems, we try and achieve net zero carbon. So now, design is essentially how we integrate all these into a whole. Now, this is easier said than done, but this is then the challenge of ecological design. How do you bring all these together as comprehensive as possible, as benign a way as possible, and as seamless as we can, without having a significant impact or with zero impact on the natural environment? And so our work starts with what we call ecocentricity, which is designing the built environment based on the science of ecology. Now, ecology sees the Earth as covered by this thin film, which is about 12 kilometers high. And within this biosphere, there are units in nature called ecosystems, which consist of biotic and abiotic constituents acting together to form a whole. Now, added to this is our human society. Now, we are obviously part of the biotic constituents in nature, in ecosystems, but I put ourselves separate because of all the biotic constituents, all the species in nature, we are the most powerful. We can change waterways, we can change landscapes, we can change the ecology of the seas, and now we're changing the climate. Now, taking that into consideration, we make things, we make the built environment. We make more things than any other species in nature. In fact, we're cluttering the biosphere with things that we make. When you look at the amount of plastics that are existence in the seas, then you give, which you jump up in horror of the things we're doing to the environment. Now, everything that we make is mostly physical. And it is the carelessness, the lack of concern about the impact of what we do, that is the cause of environmental devastations and deterioration. So the proposition is, what if we remake the built environment and into human-made ecosystems? And then the human-made ecosystems then would interface and integrate seamlessly and benignly with the natural systems in nature. So this is the most important proposition I'm going to present today, the idea of remaking our built environment as human-made ecosystems. So now, if you look into the room that you're in, everything in that room, in that building, is just about physical except you and me and the bugs. So where is the community of plants and animals? And so to make our built environment into a human-made ecosystems, we got to balance the biotic with the abiotic. And so we need to bring the two together. We need to see how we can blend and integrate the biotic with the abiotic in our built environment. Now that is the challenge of ecological design, because the city that you're in, the room that you're in, the building that you're in, is essentially almost 99% abiotic. And so I started to look into what are the ecosystem attributes that we need to emulate and replicate and augment. And so on the left-hand side, you can see a list of them. It's not a comprehensive list, but it's a working list. Ecosystems have biological structure, it's biodiverse, it is all connected, it provides ecosystem services, it are integrated as in a natural environment, and the response to climate, you can see that different ecosystems at different climatic zones respond to the climate locality. Materials are used and recycled within the ecosystem. It purifies water. It has a symbiosis where species interact with each other in a symbiotic way. That's almost a hemostatic feedback system between systems in nature. Ecosystems produce its own food, and there's the process of succession. So these are some of the attributes and properties of ecosystems that we should try and emulate and replicate to make the constructed ecosystem, to make our built environment into a human-made ecosystem. So now let's look at some of these properties. The first one is biological structure. And it is quite evident that we need to balance the abiotic with the biotic in the built environment. Now, these are some patterns that I've mapped out. You can put all the abiotic in one location in the first diagram, in the centralized location. You can have a dispersed, spotty relationship. You can have a stepping stone relationship in the third diagram. You can have a spine with fingers. And the last one is a corridor with fingers. Now, ecology sees the last one as the preferred one because if it's connected, then it becomes a single large ecosystem with a greater pool of natural resources to be shared among the species. And by having a larger pool of natural resources, it is much more biodiverse. And by being more biodiverse, it tends to be more stable. And so my early experiment is how I can interpret these patterns into the built form. And so this was another example back in 1985. I started to put vegetation in buildings, and this is a tile that I did where we put vegetation on the periphery of the buildings. You can see the sky courts, you can see the vegetation on the side. But obviously this is not a preferred pattern, but this was a first experiment that we did in putting vegetation in buildings. Now, what happens is that we as human beings, we fragment ecosystems. We cut up the environment, we chop it up with roads, with drains, with impervious surfaces, and design needs to restore the fragmented ecosystems. And so we need to design for what are called ecological nexus or connectivity. Connectivity not just at the ground plane, but connectivity from the ground plane up to the buildings. And so this is the last pattern that I mentioned. And we started to look at how we can design buildings which are connected. This was a competition scheme that we did in Singapore back in 2002. Competition schemes are for us experimental schemes and research. We didn't win the competition. I think we got second place. And the idea was to have a ramp of vegetation that circulates around the periphery of the building that goes from the ground going all the way up to the top of the building. And so the idea was to have a building which is densely vegetated on the outside. Now, this is back in 2002. And so these were early days for us. And the idea was that this building then becomes a catalyst, a device in which you green the cities so that whenever the vegetation reaches the level of the roof of the adjoining building, then we just bridge across and we green the roof. And so this becomes a device for greening the city. Of course, it's just an idea, and I'm not sure anybody has implemented it. And so designing for ecological nexus is a crucial part of our ecological design to repair the fragmented habitats and ecosystems that we as human beings have chopped up. We tend to be very destructive ecosystems. It's like turning a cow into a burger. We fragment the landscape, we chop it up. And so to try and repair this, this is to show that ecosystems are actually very connected. We cannot see this because they're invisible. They cannot actually see it with our eyes, but you can see the different components are connected. And we should be very careful about how we cut up, the ecology of the land. And so with this idea, we continued with the ramp system that we developed back in the 2002. And here is a drawing, a concept drawing we did. So this time we put a walkway next to the vegetation so that you can service the vegetation without going through the internal usable spaces. And so this was eventually built. It took us about 8 years from 2002 to 2010 to finally get this built. And you can see this is a building that we did in Singapore called the Solaris. You can see the walkway, you can see the vegetation, the sun shading, and the glazing at the back. And the idea was that we would climb a floor with every facade. So in this way, we bring the vegetation all the way up to the top of the building. And that here it is. If you stretch it out, we call this the linear park. It is about 1.3 kilometers long, probably the longest vertical linear park in the world. But it's an incredibly boring space. So what we try to do is to create plazas at the corners. And so this is one of the plazas we cut in the corner of the building. And so that people, as they go up this linear park, if you like, they can interact with people on the inside, and you can have tables to have your breakfast or your meal or a cup of coffee, and that these are the plazas that we cut into the corners of the building. The building is actually two blocks which are linked by this facade, and is on a master plan which was actually originally designed by Zaha Hadid. And the two blocks are linked by bridges, and in between the bridges is this atrium in between. And above the atrium, I have an operable glass roof, so that this atrium is mixed mode. It is not fully air conditioned, and you just have cold air being blown into it. And that on a normal day, it opens, and if it rains, the sensors automatically shuts these glass louvers, and you can see it's sealed to keep out the inclement weather. Now, we have a number of experiments in this building. One of the experiments is what we call the diagonal light shaft, which is a shaft we cut across the floor so that from the bottom of the street, we can look up and you can see the upper parts of the building. And on the left-hand side is the simulation of the daylight entering the building. And the red square on the left part of the diagram is the light shaft that goes down to the bottom of the building. Another experiment we have in this project is what we call the EcoCell. EcoCell is a device that we bring the vegetation all the way down to the ground floor, and down to the basement. And here it is. This is what ecocell looks like. And at the bottom, we can have a bioswale or John Todd calls it a living machine. Now, so that is to try and bring the BAT constituents and the abiotic together. The next is to how we can advance and design for biodiversity, which is one of the properties of an ecosystem we should try and achieve. Now, on this diagram, it's just a simple diagram that shows the level of biodiversity at different parts of the world, at different latitudes. And at London, you're about 52 degrees above the equator. It is not very biodiverse as it is, as you can see in the equator, right in the bottom there. But this is a useful index to look at to identify the level of biodiversity. The purpose of ecological design then for us is to create habitats within the building and the development. And the habitats can be green roofs, can be vertical greening, can be green sky courts, green atriums, can be green areas of the ground plane, and green links to the hinterland, and as the ecocell. This is a project that we completed a few years back, and this is to illustrate how we design for biodiversity. And the squares illustrate the different habitats we put into the building. And if we map out all the habitats, these are the red areas illustrate the habitats in this project. And so we prepare what we call a biodiversity matrix, which is this diagram. And so the first thing we do to enhance the biodiversity of the locality is to create habitats. Once we create habitats, we start to fill it up with species, and we try and identify species that will not be hazardous human beings that are native to that particular locality. And we do research in the ecology of the locality to identify the species we bring in that we put into the habitats. Next is then would be to try and identify the flora species that will attract the faunal species. And so this is the third level of research. And finally, we look at the interaction of the flora and the fauna with the habitats. And from there, this becomes the basis for designing the landscape conditions. And in this way, the whole building then becomes a living system, becomes what we call a constructed ecosystem that contributes to the biodiversity of locality. Now, this is the floor plan of the two blocks. They're almost symmetrical. They're sort of V-shaped towers, and with a promenade in between, and that it lies along this axis between the public realm and the waterfront. And the waterfront is the Millennium Monument, which was also designed by us. But on the right-hand side, you can see the building. We had to split the building rather than join it together into one big complex to allow for this axis that starts from the plaza all the way down to the waterfront. And here it is, seen from a distance. The building is not in this image yet, but you can see across the land, and that's the Ministry of Finance building in the background. We wanted to break away from the facile appearance of a modernist building. And so we tried to shape the facade and to facet it. And so the idea was that because the building lies in the axis leading to the Prime Minister's residence at the top of this axis, you can see the Prime Minister's residence on the top right-hand side. We thought we'll make this into a jewel, a gem in the locality. And you can see the metaphor of the gem on the right-hand side. And that to give a memory of the cultural identity of locality, we use a pattern which is called the Songket pattern, which is an image, which is a pattern that the Malay community used for their fabric. And so this is the pattern, becomes a fitted pattern on a glass. We have a series of glass panels. They're not butt jointed; they just have an air gap in between, and this is put on facade of the building. Now there is a gap between the outside skin and the inside skin. So it's a double skin building. You can see the corridor in that red square rectangle on the left-hand side. And then the second image shows the corridor. You can see the outer skin, and then the inner skin, which is flat. The outer skin is faceted, but the inner skin is vertical so that the office space, is not affected. And then this is the corridor in between. And the third image shows the fitted pattern seen from the outside. It is about 50% clear and 50% opaque. And the last pattern right-hand side shows the view of the pattern from the corridor looking outwards. This is the west side of the building, which is the hot side of the building. We angled it so that this protects the facade from the hot western sun. The building energy intensity is 136.18 kilowatt hours per square meter per annum. And the average office building in Malaysia is about 210.52, and our project is about 70% less. And so this is an experiment as a substitute to the conventional horizontal louvers, where we use fritted glass as a form of sun shading. And by all means purposes, this is to illustrate that it does work in reducing the solar, the energy intensity of the building by at least 30%. This is the eco-cell for this project. And you can see from, it's the final habitat. We bring all the way down from the third floor of the building in a continuous way in the ecological nexus all the way down to the bottom of the building. The eco-cell idea was developed a few years earlier, maybe about back in 2002 when we did this competition for the Kowloon waterfront. And the eco-cell is actually a void that we cut from the podium all the way from the roof down to the basement. And it brings vertical integration of greenery, provides opportunity for rainwater harvesting, provides opportunity for bringing natural ventilation to the inner parts of the building. That brings opportunity to bring daylight penetration. And of course, we have a eco machine or a biosphere at the bottom of the eco-cell. So then you've seen how we increase the biodiversity in a medium-rise building. The challenge then is how do we address the biodiversity in a high-rise building form? And so this is a project which is now under construction. The idea, the pattern that we use is the tree with fingers. And then the second pattern shows the sky clouds we have, in the building at selected parts of the building. The approach then is to start to look at the ecology around this locality, to start to look at what species we should bring back into this site. It should be native species, should be invasive species, and a species of fauna they want to bring back, and flora that will attract the fauna. And so what we try to do with the high rise is then for the lower floors, we would have a zone for dragonflies. Then above that would be the butterfly zone. Above that would be the songbird zone. And finally at the top would be migratory birds zone. So in this way, we bring, for the last two floors would be invertebrates, and then we have birds on the upper segments of the building. This is the biodiversity matrix we did for this project, where this identifies the birds that we want to bring back, and the flora that will attract these birds to this building. Now, one of the properties that we should try and emulate and replicate is the provision of ecosystem services. Ecosystem services is a term that ecologists developed during around 2000 of things that nature does for us without human intervention. And so, one of the properties of an ecosystem is the provision of ecosystem services. What are ecosystem services? Here is a list of things that nature does for us for free. We don't have to pay for it without human intervention. It's not a comprehensive list. It's a detailed list I could assemble. Nature produces oxygen. Nature suppresses pollution from the air, and nature produces pure water. And so to create the constructed ecosystem, we have to try and emulate and replicate, this set of activities, set of services. Now it's a tall order, and so I try to do as much of this as I can in some of our work. And as you can see here, nature fixes solar energy to produce energy for ecosystems. Nature sequesters and absorbs the pollutants in the air. And so these are things that nature does for us. So one way to provide this is to increase the biotic content of our buildings. And so for the earlier building that you saw, what we try to do is, besides putting the vegetation in the ramps and the vegetative ramps that wraps itself around the building, we have a garden in the middle of the halfway up the building, which is the mid-level garden, and then we continue to bring the vegetation up to the roof. So this is a roof garden at the top of the building. But this is not entirely satisfactory. And nature, and even though we can, extend it as much as we can, in Singapore, they have what you call a green index. And it should be, the index is 6, that means the amount of vegetation in the building over its footprint, over the land area. Now here we achieve an index of 12.2, which is, twice what is required to get the part of the local green rating system. And so the green rating system for any locality is just a figure that we try and surpass as much as possible. And so how do we provide ecosystem services? Because it is totally impossible for us to emulate the way nature produces oxygen. We emulate in 100% the way nature absorbs pollutants. So the idea was that if you cannot beat it, you should try and join it. So the suggestion is to juxtapose the biotic constituents to augment the ability of our built environment to provide ecosystem services. And so the idea then was to try and weave nature into the built environment. And this is the pattern that you can see on the left-hand side. We have a series of corridors and fingers that eat into the built environment. And this is the pattern we did for the Reunion Island in the Indian Ocean, which is east of Madagascar. And what we have is a series of green fingers which eats from the waterfront, which is the corridor, and the fingers eats into the built environment. On the right-hand side, you can see the urban areas. And so the idea was to weave the green into the urban areas, as you can see this diagram. And if you superimpose onto our master plan, you can see how they interrelate with each other. You can see the green fingers, you can see the urban areas, and that how the green fingers are brought right cheek by jowl with the urban areas so that you can provide ecosystem services right next to the urban areas. So this is one way of providing ecosystem services with the aid of greenery right next to the urban areas. We took a distance of about 30 meters, for the urban fingers and 20 meters for the green fingers between one and the other. And then the edges of the urban areas should be serrated. And this is a diagram that shows how the green areas, which is the red lines, and the urban areas is the black. But we have roads cutting across, and we cannot bifurcate, the green areas. So we develop what we call eco undercrofts that you can see on the left-hand side, where the greenery goes underneath, and then the roads go on top. For the edges, it should be serrated so that the species that we bring back to the locality have opportunities to hide, opportunities to find refuge, opportunities to mate, and opportunity to find food. Now, one of the other ecosystem services is the how nature provides pure water, cleans the water, and that this is one of the ecosystem services that nature does for us. without asking nature to do it, and asking, and without human intervention. And so obviously this is the hydrological cycle that of how water flows in the biogeochemical cycles. And this is the master plan that we did in Bangalore. And that's the forest reserve on the right-hand side. We brought the vegetation as a series of fingers across the site. And so that this then tries and link the forest reserve to species to adjoining sites to reconnect nature to enhance this ecological nexus. And so this is the master plan. You can see, the series of fingers that cuts across the site, and this is the water distribution system. And in the red, in the white squares are the detention ponds where the water goes back to the ground. So we need to recycle the water as much as we can. So internally, this is a diagram that shows how we could conserve the water inside the built environment, reuse it, recycle it as much as we can. But those that we cannot use, as you can see in the red arrows, we should bring it back to the ground to recharge the groundwater. And the different ways of doing this is in a series of diagrams on the right-hand side. Now, for the black water, we should try and treat it with what we call constructive wetlands. There's a series of ponds so that it flows from the settling pond down to the wet woodland, to the treatment marshes, and to the polishing pond right at the end, so that by the time the water moves from the first pond down to the last pond, it is almost potable. And so in this way, it is a natural way of treating water rather than through mechanical means that requires external sources of energy. Now, what happens is that we have roads that cut the greenery. And so if you look at this pattern, then the greenery then is the continuity of the greenery is affected by the roads. So the solution we have is to use what we call eco bridges. And so these are the bridges that cuts across the road so the vegetation can go from one part of the site to the other part of the site, without being affected by the roads. Now, nature fixates solar energy and creates energy for the ecosystem. And so, however, our human society, we're dependent on the use of fossil fuels. And so if we try and reduce the use of fossil fuels and try and design what we call a net zero energy and net zero carbon environment. And so this is one of the factors that is in our 5 sets of factors that we need to consider in ecological design. And so, yes, you can see this diagram again of ecosystem services. In nature, it fixates the production of solar energy. Now, for designing a net zero energy is essentially a series where you go from passive mode or bioclimate design to mixed mode, to full mode, to productive mode. So productive mode means you produce your own energy. And this is, if you like, the whole process. But you have to start from optimizing each of these stages. Otherwise, if you go straight to productive mode, you'll miss some stages, which will then could make it into a high energy building. Now, this diagram shows, if you like, the comfort conditions, the external conditions in the winter and summer. In the winter, it is you have a cold winter, as in the UK, and you have a hot summer in that blue diagram. So this is the outside climate. The red line shows what engineers want to do for us. They want us to have consistent temperature, humidity, edge, and throughout the whole year, which is a high energy condition. So designing for low energy starts with what I call bioclimatic design. The strategies for bioclimatic design on the right-hand side, by proper orientation of building, by built form configuration, by facade and enclosure design, by optimizing ambient energy, and by using natural ventilation. Now you can see bioclimatic design can improve the comfort condition. You can this white line just a little bit. There's no way that bioclimatic design can ever replace that red line. So the next stage is that bioclimatic design is defined as improved comfort conditions without the use of any external energy systems, without the use of mechanical, electrical systems. The next stage then is what I call mixed mode, which is some mechanical electrical systems, such as using ceiling fans or exhaust fans. And so you can further improve the comfort condition. So this is the use of mixed mode. So you go from external condition to passive mode to mixed mode. And then from there, you have what you call productive, full mode, which then for full mode to systems to be effective, they have to be smart systems, and they have to be extremely efficient. And then, of course, the final one is productive mode, where you produce your own energy. And so here's some illustrations of how this could be implemented in architectural design. Back to this project that we did. This is the tower back in 1985, and you can see the plan. On the left-hand side are studies that show how the core position can contribute towards designing a low-energy building. Now, what this diagram shows from all these sort of orientation, configuration, whether it's a central core or a side core, that the core on the east and west sides in the tropics reduces its energy consumption. And the most efficient configuration is the one in the red square, because by doing this, the core then becomes a buffer between the hot east side and the hot west side. And most of the day, the sun is above. And so if you like, this is the ideal configuration on the high-rise building form, and to make it into a low-energy building. The next would be, another example of passive mode would be what we call umbrella building, because then on the third of the day, the sun is above. And so the idea would be to have an umbrella, which is as a device to keep out the sun. Now, umbrella for me is an incredibly useful device because it keeps out the, it's cybernetic. If the wind comes from one side, you just tilt the umbrella to that direction. If the sun comes from the other side, we tilt it to that side. And if you like, my golden chalice is to design a building which automatically has a canopy that shifts and adjusts depending on the climate conditions and the position of the sun and the wind and the rain on that particular point of the day. And so this was a building that we did back in 1985, where we put a louvered umbrella over the entire building. And so the idea was to let in the morning sun, which is angled, and then the building uses about 42 kilowatt per square meter per annum, compared to office building which uses a normal building which uses about 131. And that this is the east side, which lets in the wind, which is lets in the morning sun, and that and then this is another canopy building which is the guardhouse, which creates a space in between. And here's another one where we have for a station that we did in Beijing, where it uses modules that are interconnected to create a canopy over the station. There's another canopy we designed over a station, and that this is a canopy. This time we use fritted glass that we used in the other building project. We put it now horizontally over the university core. Now, the next level after bioclimatic design, or the passive mode, is what we call mixed mode. And this is the project we did in London, which is in the Great Ormond Street Children's Hospital extension. And we're trying to use natural ventilation to increase the mid seasons, which is the comfortable seasons of the year, which is spring and autumn, and use natural ventilation to extend it into the winter months and into the summer months to reduce the period for cooling in summer and the period for heating in winter. And so in this way, it becomes a low energy building. Now, this is the extension that we did for the Great Ormond Street Children's Hospital, which is in the Bloomsbury area. On the right-hand side, we put a glass flue on the facade, and it has a valve on the top of the building and a valve on the bottom of the building that controls the air going through the building. And in between the building, in between floors, which is where the natural ventilated areas are, which is occupied, which is operated by Walt Disney, and this is a mixed mode building. Now we did the same thing for a project in Beijing, which is 39 degrees above the equator. This is a renovation to an existing building, which is south of Beijing in the Xiong'an area. And here we punched holes on the facade, and then we create a new flue on the outside so that this sucks in the air in the mid-season and right to the top of the building. And you can see on the right-hand side the simulation in the building and during the mid-seasons. And so finally, productive mode is where we actually make our own energy. And this is removed from external conditions to passive mode to mixed mode. And before we reach full mode, we have productive mode, which is that dotted line that you can see here. And so here's the building that we are under construction now. And you can see what we try to do is to put photovoltaics on the roof. And to make it work, you can see the photovoltaics extend over the building, because to make it energy independent, it has to be at least over 50 to 60% of the gross floor area in order to acquire enough solar energy to make the building energy independent. And so this is the building. Then you can notice the green facade on the south side of the building. And the building is done in brickwork. And this is the productive mode building. Then the thought, what happens if we make the whole building into a powerhouse that it generates own energy? So the idea then was to use glass which has photovoltaics embedded in it. And this entire building is then covered with this photo embedded glass, so that the building itself produces its own energy. It is positive and in the high-rise built form. And this is the building that we hope will get built. And so we need to design for net zero waste and emissions as one of the properties that you can see of the ecosystem. And so on the right-hand side is this diagram. What happens of our built environment within the biosphere? The biosphere consists, if you can see, of ecosystems, the biosphere and the climatic processes, and the global energy material resources and the existing built environment. And the built environment itself is that square in the middle, which has impacts on its first environmental impact, that's operational impact, and it's an M impact. And we need to reuse the material as much as possible. On the left-hand side are the inputs into the built environment of energy, water, materials. On the right-hand side are the outputs. What we need to do then is to close the loop as much as possible. The outputs are then brought back, reused, recycled, and reconstituted, and brought back reintegrated back into the biosphere. This is a scheme that we designed in Berlin, where the idea was that you use recycled materials from the city into the building, on its facade, on the structure, and then the waste materials will go back to the recycling center, at the top, and this also accumulates recycled materials from the city itself, and so recycling has to be done at a citywide level, at district level, so that materials are reused and recycled within the built environment. Now, designing for systems regulation, or what I call homeostasis, then is what nature does, which is regulates the chemical constitution of the atmosphere. It regulates the chemical composition of the oceans and so forth. And so the idea was then is to make use of intelligent systems to monitor the natural environment, so we can take corrective action straight away, and to make use of the satellite systems, so that in this way we should have a rescue center, so that whenever any part of the planet is affected and which is in danger of being devastated or impaired, we can take immediate action. And so the principles I presented today are basically twofold. The first is what I call ecocentricity, which is designing based on the science of ecology. And the second is ecomimicry, which is remaking our built environment as human ecosystems by emulating and replicating its ecosystem attributes. Now, I'm going to end now, but I want to discuss what about the human society, because human society is our social systems, our economic systems, our political systems, institutional systems. Now, if we project in the future, what if our design is 100% perfect? We have, all the systems are recycled, we use renewable sources of energy, we're able to emulate and replicate the properties of the ecosystem. That means the built environment is designed in such a way that it is responsive to the natural environment. That leaves us as human beings. So that's the question. Now, what if we human beings don't behave, we're wasteful? And so ecological design is not one of designing the built environment. It requires behavioral changes of our human community. And that is the challenge that we have to address, in addition to be able to address all the impacts of our built environment on the natural environment. Thank you very much.